All right, like the title says here, we're going to be talking about massively parallel encoding in the cloud, specifically for adaptive streaming. So obviously, we're here today because we have a problem, right? Modern codecs are getting more and more computationally complex, which means that they're taking longer than ever before and obviously requiring more and more compute per assets. On top of this, adaptive bitrate streaming adds even more complexity to these as we are encoding the same stream multiple times for different sorts of devices. So today we're going to look at different methods that we can use when we are encoding video to help parallelize the process. We're going to go over some common pitfalls that we can run into when we parallelize encoding. And then we're also going to take a look at some computational efficiencies that we can gain by recycling analysis data with these multiple resolutions. So first, we're going to look at a very brief history of encoding. And what we see here is that we have an increased need for different streams. So in the antiquity, we may have had just one stream. It's MPEG-2 SD. We kind of move on to the Middle Ages, where we now have SD and HD content. Maybe we have some that are in MPEG-2. Maybe we have some things that are encoded in H.264. Then we come along with video streaming and adaptive bitrate, and now we have a near infinite combination of streams that we can have. We have resolutions from 360p up to Ultra HD resolutions. We have multiple different codecs. We even have different transformation matrices for things such as SDR versus HDR video. So our problem is getting more and more complex. We start off with a appliance style, kind of drop it into a data center, does one stream sort of video encoding solution. And then as commodity hardware continues to get better, we can move on to CPU encodes and possibly with GPU acceleration. But as things are getting more and more complex, we have an increased number of streams. The next step is moving encoding to where we have even more compute power, and that's going to be in the cloud. So thus we get to massively parallel encoding. So it's a split and stitch approach. What we do is we take our mezzanine video on the input side, we break it up into some subset of frames, we encode each of those subset of frames individually in parallel, and then we stitch them back together and we finally make the compressed output. Now, the compressed output doesn't necessarily have to be one big long file. You can also represent it with an ABR manifest and keep it as separate segments if you need. So the first step is going to be, how do we split up the video? The initial kind of easy way to do it is you take the video and you split it into fixed size chunks. A certain number of frames, also a certain duration of video. The nice part about this is it's consistent and it's easy, but unfortunately, you can start to have some quality issues potentially around your cut points. For instance, if you make a split where you have a scene change boundary in very close proximity, you may be getting inefficiencies in the encode, or you may be able to see some quality degradations around that point. So a more advanced way to split up the video is to split it up by scene on the input. This isn't necessarily a new idea. It's very similar to Netflix's shot-based encoding, where they took scenes and they split the input video up on scene and then encoded each of those scenes. But we recommend taking the video and doing multiple scenes together, some integer number of them, to target about a minute of video. And that's because we see some computational efficiencies from those larger jobs. So what we can see here is, with the plot on the right, is that you can see an increase in overall frames per second for encoding for the job if you start to target larger jobs. Obviously, this has some sort of taper off point, but if the job is large enough, then you really see a negligible computational overhead from the encoder setup and teardown point. For this reason, we actually see encoding jobs at actual segment length, so for instance, a very short 2-second length. These are reasonably harmful to the overall efficiency and throughput of the system, which is why we've been targeting roughly a minute of video for the encodes. So this kind of brings us to an overall diagram of what we're looking at here. And we have an input mezzanine video that can be stored in an on-premises cloud as in a distributed file system, and then we can also have a public cloud component that you can schedule jobs on as well. And then the scheduler just does a basic scheduling where it looks for a certain amount of compute and memory needed by the encode job and can schedule it on machines accordingly. So what benefit does this get us? Well, encoding traffic is inherently bursty. In this plot, you can see over 180 days of encodes, there are only 4 days where you're above 40% of the capacity. So we can see with a split and stitch sort of approach, we can see better resource utilization. We can see better CPU utilization on an individual host because a single encode from start to finish may not necessarily saturate all of the cores on a large server. We can also see better overall hardware utilization. So this means that we can size an on-premises cloud for the nominal load that we're going to see over encoding. And then if we get one of those big bursty days, we can then send just that chunk of encode off to a public cloud in order to get that encode done. It also saves on bandwidth. We're not uploading an 800 gigabyte ProRes file to the cloud unless we actually need to. We can just do the short, small chunk. So this also leads to workflow improvements, and namely a very reduced turnaround time. Since we are splitting up the video into individual chunks, your theoretical encode time, given enough machines, is that just the amount of time that you can use to do that one individual chunk. Which is much more reasonable than doing, a 2+ day encode on a cinematic length movie. It also gives us much better resilience because, once again, with a 2-day long encode, if you run into an issue with the encode at the end of that encode, you may have lost 2 days of work if you're doing the entire thing from start to finish. The same thing goes to if you have an entire node that goes down that's running multiple 2-day long encodes, you've just lost a whole bunch of CPU time that you otherwise wouldn't have to if you use the split and stitch. So, stitching. Ideally, stitching video together would look like this. This is a picture of Unix cat, but as you can see, this is the naive solution. So, what's the issue here? If we just take an encode and we cat the files together, it may break hypothetical reference decoder constraints. Namely, that the 2 encodes for the 2 different chunks are probably encoding in parallel, and they don't have knowledge of what the coded picture buffer state is of that previous chunk. And so what you can get is a disparity between the actual CPB fullness and what the assumed CPB fullness is. And so you can actually potentially build a growing disparity between those two as you stitch those segments back together. So what do? We can start by specifying at the beginning and the end of the encode what the CPB fullness state should be. This is great because there's really no computational cost associated with it, but once again, you can start to have some potential quality issues around that stitch point because you may be artificially lowering the amount of bits that you can allocate. So, better stitching. What you can do is you can provide 2 overlapped chunks, not the entire segment, but enough that at the beginning of the encode, you can start to build a realistic CPB fullness level. You can then encode the frames for your actual chunk, and then you can have a segment at the end that's used for look ahead, so you end at a realistic CPB state as well. And then obviously the look ahead for the previous chunk applies for the beginning section for the next chunk. So what does this get us? Obviously there's some overhead associated with this. But the overhead is reasonably constant and can once again be built into those chunks that are long enough that you may not pay too direly for it. And the benefit that it gets us is a very constant quality across the encode at those stitching points with really no perceived degradation where we stitch the video back together. So thus far, we've been talking about doing an individual encode of the asset. And I said that we were going to talk about adaptive bitrate streaming. So obviously, additional compute required because in order to fulfill something like Apple's recommended Ultra HD HLS bitrate ladder, we're looking at 12 separate encodes, right? These were typically done as independent encodes, which obviously multiplies your amount of compute that you need by 12. So the thing about this is that the underlying content is perceptually the same. You have the same frames, you have the same textures, you have the same objects, the same motion, and all of these are highly correlated. They're probably done, all of the different resolutions are probably taken from a single high-resolution master. So why do we insist on doing the same thing 12 different times? So we propose that you can recycle the encoder decisions from low resolution to high resolution. You can recycle the motion vectors and the quad tree structure, write it out into an analysis file, scale that, apply some refinement, and then use the data from that, which are the computationally complex portions of the encode, to apply to higher resolutions. It works for resolutions that are multiples of 2, right? So in this diagram, we're seeing that we have a 540p encode. We do that encode, we write out the analysis file, and then we can apply that to 1080p, potentially write out another analysis file and apply it to 2160p and on up the chain. So why do we refine? Some of the modes, such as skip merge, can't be evaluated at the lower resolution. And there are also rate distortion optimizations that may be different at the different bit rates for the video. So in X265, for instance, the different levels of refinement, you can start with no refinement at all. So you just scale the video, reuse the CU and PU information, and then do your encode. The level 1 level of refinement, you split 16 by 16 CUs into the 8 by 8, and then you take the scaled motion vector and you do a minimal amount of refinement. Level 2 is level 1, but we reevaluate skip merge. And then level 3 is level 2, but we completely redo motion estimation. And obviously these have an increasing cost in terms of compute and speed depending on which one you select. As such, there's also a dynamic level of refinement, which based on the underlying content can choose between level 1, level 2, or level 3. So what does this get us overall with this refinement? We see at least a 2x speed increase for the fastest level of refinement and no degradation in quality. The dynamic refinement obviously is a pretty good average of the different levels of refinement here and tends to be a pretty good trade-off. So this allows us to build a graph that we can do for the Apple's recommended 12-step ladder, where we have two different types of analysis. We have the full analysis that can apply to resolutions that are multiple of 2, and then we also have to have frame alignment across all of the different resolutions for streaming clients, and so we also need a QP file, which is just a simple frame number and frame type to keep all of the encodes in line. And then frame type is obviously aligned for the analysis files across all of those. So any of the encodes that you can see here that are in vertical columns can all be done in parallel because they have no dependency on one another. The analysis files can be applied between resolutions that are multiples of 2 or potentially to a lower bitrate encode of the same resolution. So what's the summary here? Split and stitch, it allows us to encode video much quicker, and and as long as we keep our eye out for those kind of common pitfalls around the split and the stitch points, we can keep a very high quality video output with increased system resiliency and vastly increased speed. And then when we push that further and we do analysis reuse, we can see drastic performance gains out of this with no noticeable degradation in video quality, and using the resolutions from a low resolution to a high resolution decreases the overall number of cycles that we actually spend during our encode. And the nice thing about this is that this analysis reuse can be applied to any motion compensated video codec. So that means that H.264, AV1, and VP9, this same sort of approach can be taken. Thank you.
So I guess there are a few questions after this presentation, so please feel free to come up to the mic and ask your question.
Couple of quick questions. Do you keep the frame rate same across the resolutions, or do you go from 60 to 30 frames per second?
So thus far, we've been doing the analysis with the same bit rate, or no, I'm sorry, the same frame rate. So we haven't been doing changes between, like, applying the analysis between 24 and 60, if that's what you're asking.
And 30, 720p 30, and there is also a very popular format, 720p 30.
Sorry, could you?
720p 30?
Yeah, so 720p 30, I'm not sure, maybe I'm misunderstanding your question. Could you say it again?
In your ABR bouquet, you will also find 720p 60, 720p 30, 540p 30, and so on. So they also sometimes change frame rate. Have you experimented with the frame rate change also?
No, we haven't looked into experimenting with frame rate changes yet.
Okay, that's fine. And also, do you have any idea, will it be helpful to do the refinement, or you might as well start from the scratch?
I mean, since we haven't looked into it, it's not really something that I can provide, you know, any.
Can you go back to your stitching, the smart way you were doing it?
Which one?
The stitching, keep on going back. Stitching that you were doing when you were putting the streams together. Yeah, right here. Now, I got confused here. You don't have, you're doing the top and the bottom in parallel, right? So you don't have the luxury to go till the end to figure out what your CPB size will be. So how will the next parallel encoder know?
So you're providing more frames underneath from the original input video. So these are running in parallel, but this is showing an overlap in frames on the input side, and since they were both taken from the same mezzanine source, you should have frames on either side of that you can provide.
By the time you reach the orange on the top, the bottom should be also running in parallel, right?
Right. Yeah, this is so both of these would or could potentially be running in parallel. And
you don't know what should be the beginning of green of the bottom be.
So
you don't know what the frame buffer size should be in the bottom portion, because it is not sequential as you show. It is really in parallel. You're running these two encoders in parallel, the top and the bottom, right?
Right. It's a predetermined.
So it's a predetermined
set of frames just to build up the buffer state, or end at the reasonable buffer state, right?
Yeah. So predetermined is one you had in the previous slide. So I was wondering what's the difference between previous slide and this slide, the one before, before you went to go one more back.
This?
No, even before you get to better stitching, one more back.
Cat?
Yeah, knife switching, right? Because after that you had where you have a predetermined buffer size. And you rightly pointed out it has a problem. It will degrade the quality. So to avoid the quality degradation, you do extended look ahead. But extended look ahead does not look like will be of any help, because by the time you reach that look ahead, the second encoder has already left the station.
So all of,
Or maybe I can catch you after the presentation.
yeah,
Okay.
maybe we can sync up afterwards.
All right.
So maybe in between I can ask probably a simple question. You showed during your presentation a graph with the utilization of the encoders and certain peak values. And I believe you mentioned the number 40%. Is this 40% also usable to say, well, this is the amount of encoders we need to have on site, and if you go above, this is what you typically push to the cloud?
Yeah, that's correct. So you would want to, if you wanted to do this in an on-premises or like a hybrid cloud model, you would want to size your on-premises cloud so you can keep up with what your assumed normal volume is, and then anything that, you know, if you start to fall behind in those jobs, then you can push to an off-premises public cloud.
And due to the fact that you're using parallelization, I guess with parallelization you have a sort of overhead to organize all the parallel streams. So what is typically the bottleneck that you think, well, don't do this, otherwise your solution starts to slow down?
I mean, in terms of the organization and the orchestration of all of those, realistically, pulling the video in and splitting it up and making those jobs, you know, you're limited kind of by a single process that is, you know, doing that splitting up and the organization there. So since they're pretty big files, it's probably mostly whatever your file I/O is, or if you're doing it all on public cloud, doing that push up to the public cloud, and of course, money. How much are you willing to pay for your encode?
So any other questions from the crowd here? So we're very early. Apologies for this, but anyway, thank you for the great presentation, and let's give him a round of applause.
Thank you for watching. If you enjoyed this video, please tap the like button and also subscribe to our channel to receive notifications when we add new content. For more information about us, please visit SMPTE.org. We'll see you next time.